There's a basis for energy measurement, namely absolute zero, where energy has no temperature, or matter has no temperature, and it's in a crystalline form. So that's our basis. So in some of the calculations we do even for heat transfer, we have to have an absolute reference. So the absolute reference is absolute zero. And we'll stay in English units, so minus 460 degrees Fahrenheit is absolute zero. Okay. And this is the average temperature of say a beaker of water. Okay, so one of the important things to understand with temperature is temperature measurements are measuring average molecular energy. They're measuring average molecular energy. So they're not measuring the energy of every molecule. And therefore, if you were to look at the energy of every molecule, you get a curve like this. So if we look at this 100 Kelvin one here, which is cold, this curve right here. So this is very cold liquid. The temperature I measure, the mean temperature is going to be right. Whoops, the mean temperature will be right here. It'll be right here. That'll be the mean temperature. But there's particles out here that are faster than particles here. So these are molecules, they're vibrating. They interact with one another slightly, and especially if they're polar, you get these van der Waals forces that we're looking at that tend to make molecules stick, and they kind of drive phase change. As I heat this same beaker with water up, I heat it this way. This happens to be hydrogen. The profile looks like this. So you have just as many molecules as you had before, but the mean temperature now has moved up to here. So that's a temperature increase. And that's kind of a lot of data. If we look at this next one, you can see it a little more clearly. So you have two temperatures. You have temperature 1, which is colder, right here, and temperature 2, which is warmer, right here. So if you don't lose any of the molecules, the area under the curve, if you were to integrate these curves, you would have the same number of molecules. But temperature 2 is warmer, so there's more temperatures at this high energy realm. And this high energy realm is really important. These are molecules that can evaporate. So you can say, how can a glass evaporate at room temperature? How can I put a glass of water out and suddenly in a day or two there's no water left? And because everything's at room temperature. Well, you have this case where many of the molecules operate at a very high energy state, and those are the ones that go into the gas phase. So this diagram that you're looking at right now is really important for understanding temperature. If you don't understand this diagram, you really don't know what temperature actually is. So these dashed lines are the mean temperature, meaning there's the area to the left and to the right are equal. So T1, I would have a temperature, say, 50 degrees, right? And if I heat things up to, say, 80 degrees, where the blue is, that's truly what my thermometer is measuring, but the actual profile looks like the blue curve. And consequently, you get more things evaporating. Okay, and this is looking at phases. And again, this is a helpful graphic, I think, because it's showing you what happens between phases. And of course, when you have phase changes, there's no change to the molecules themselves, but the question is, why do they stick together? Why do you have these phase changes? And as hopefully you saw in the reading, what's occurring is the molecules have kinetic energy, bouncing around. And the only thing that keeps them from bouncing around are two things. One, lowering the energy, cooling them down. They don't bounce around as much. And secondly, if something grabs them. So if there's a force acting on another molecule, it will grab it and stop it from vibrating, sort of like a magnet. So if you have, like you dragging or grabbing the collar of your dog or something like that, it's scampering around. If you grab the collar, the dog doesn't scamper around. And in the case of molecules, what those are weak surface forces. So they're typically van der Waals forces. And these are forces, there's different categories. Maybe you've heard of hydrogen bonding too, which is a sort of another type of surface force. But a good mental model is to think of molecules as having stickiness, and you could think of them as magnetism, but it's better to think of them as being sticky or actually electromagnetic. So water, which is what we're looking at here, the two red dots are hydrogens and the blue dot is oxygen. And oxygen or water has this shape that's like a dipole. It has a plus side and a minus side. So the hydrogen is a plus side and the oxygen's a negative side. So these produce little weak magnets that cause other molecules to stick to them. So if you have certain topographies like hydrogen is good or helium, where they're spherical, they tend not to ever freeze because they don't have that polar quality to them. They're perfect little spheres, kind of like you thought about molecules being when you were very young, maybe in elementary school. Molecules, or of atoms being just little spherical things, and molecules maybe being spherical things. When in fact, the shape of the molecules is very important. So the morphological connection between phase change and energy is really important. So if something's really polar, it's going to be sticky, and it will want to create a liquid or a solid phase more readily than other molecules. So that's why it's hard to freeze certain things like hydrogen, because they don't want to stick. Okay. And again, I'll be happy to entertain questions about that later. Here is another diagram with the British spelling of vapor, just to show you how cosmopolitan we are. And what happens is you have this equilibrium phenomenon where things are going into vapor phase and going into liquid phase. So if you look at this beaker on the left, you have water that's sealed in a beaker, and some of that water, if you recall from the temperature profile, some of that water has really high energy state, and it wants to go into a gas phase, and it does. And some of the gas phase water out here wants to become a liquid. It loses its energy, and the stickiness of the surface molecules draw it back into liquid phase. So you have this equilibrium that goes on, and you can play with this equilibrium, which is really an interesting thing. You can play with it by pressure. So if you apply more pressure, like you do in the radiator of your car, you basically squish the molecules closer to one another. So these surface forces, the stickiness factor, comes into play. So if you have these dogs scampering around in your apartment, and if you make the apartment progressively smaller and smaller, the dogs get closer and closer to each other, and pretty soon they can't move. And if they have sticky fur, they'll stick to each other with ease. So I think that's kind of a good mental model, this notion of you probably see my fist, but the bouncy molecules, where the molecules are bouncing around as a function of the kinetic energy. All right, this we did not talk about. I did want to point it out because it's really important. It's the refrigeration cycle, and don't want to elaborate on it too much, but it's kind of neat because you all have refrigeration systems of some sort. So on the y-axis, you have pressure, and on the x-axis, you have enthalpy, which is basically energy with a pressure, well, an ideal gas determinant, but we won't look at that. So this is how you have this curve that shows you different phases and how these cycles work. And all I wanted to mention with this, I do have a diagram, or sort of the illustration of what this does for you in another diagram, is I can change phase by changing pressure. That's how your refrigerator works. So your refrigerator at your home has a liquid and a gas running in it. And what changes it from a liquid to a gas is not temperature, but pressure. And you have a little compressor in the back of your refrigerator or your air conditioning unit or whatever. Usually they're hermetically sealed, they're like black dome things. And they change the pressure of the refrigerant and turn it from a gas into a liquid. And then when the liquid evaporates in the evaporator, it cools things down, and you take advantage of that. So there was some reading on that. I don't want to belabor that. It's actually an interesting thing to look at, but I don't want to do that here now because that's sort of outside the scope we're looking at. But this is sort of an example of thermodynamics in action. So what we're looking at here, and what we'll do in class, assuming we meet, is we'll go and tour a mechanical room and take a look at this equipment and talk about refrigeration phase change. So that's my hope. But I want to show you this diagram anyway. Underneath commercial buildings, typically, or on the roofs, you have boilers or chillers and boilers. So here's a chiller right here, and this makes cold water. And inside the chiller, you have this refrigeration cycle going on where it uses a refrigerant of some sort. We actually used to do labs with not R22 but 401 and some of the more safe HFC refrigerants, and that's all contained within the chiller. And so it's taking this refrigerant, it's compressing it, turning it into a liquid, it's expanding it, and it's cooling water. So what it does then is the heat produced by this process goes out to a cooling tower, which isn't shown in this diagram, but you have to get rid of this heat, and it goes out to a cooling tower. And yeah, I hope we can visit one of those. And even if we can't in this class for some reason, we'll do it sometime. So that's how you get rid of heat, and then you spray water in the cooling tower, and there's different types, but typically they have a fill, like a plastic material. You spray the water on there, and the small droplets evaporate more readily. There's more surface area exposed, and the water actually cools down about 10 degrees Fahrenheit during the operation in the cooling tower. So it's a really good way to cool things down. That's how you get rid of the heat produced by refrigeration. And then what you do is you send the coldness to these air handlers, and you do it with water because water is safe. You could do it with refrigerant, but water's safe, so you have these pipes going out throughout a building that contain only cold water. So again, if there's a leak or something like that, you don't have to evacuate the building, nobody dies, all things are well. But it sends this cold water to a coil, and a fan blows air over the coil, and that cools the air. So that's what this is. It cools the air, goes through here, and it goes out into your office or whatever it wants to be cooled. And sometimes there's a rats. All right, 10 minutes. Last time it let me upgrade. So if not, I gotta talk faster. But I'll send out another invite if we run out of time. That's how much time we have here. Okay. All right. Anyway, that's how that works. So they're really neat devices. And what happens too as the air goes through the air handler is the coils are thick enough that water condenses too. So if you just put a really cold coil into what's called an air handler and blow air over it, it will get cold, but the water won't condense, or will condense in the ductwork and cause it to rot. So there's actually a good science connected with comfort cooling. And the same is true with heating. The boilers send hot water to these air handlers and work the same way. Okay, this is the unit up at Cornell that we had talked about briefly, where you take in cold water from the bottom of the lake, run it through heat exchangers right here. And this is actually what they look like. This is a photograph I took. There's a bunch of air handlers, and then you send it back out to the top of the lake. So the delta T between the bottom and the top isn't very high. And then that's the lake side. And then on the campus side, which is up here, you send the chilled water 45 degrees up to campus. You run it through all those air handlers that I showed you in the last diagram, and then you return it back to these heat exchangers that in turn cool the water from using the lake water. So all you need here is a pump for the lake side and a pump for the campus side. 2 pumps. And what they have, these are some of the pumps here, and these are just redundant pumps. And well, they're not all redundant, but you bring these heat exchangers on as you need them. And these are called low Reynolds heat exchangers, which we'll look at when we look at heat transfer. And Reynolds number is really important, and it's just a way to get you in the club. Basically, it means low speed. This is really a geeky diagram. I don't want to make your eyes fuzzy, but I do want to, if you're into ice skating, all I wanted to point out with this kind of quickly is if you see, let me go with red on this. And, okay. If you are ice skating and you're at 1 atmosphere of pressure, you're right here on this phase diagram. When you put those sharpened blades on the ice, you increase the pressure up to here. And you turn the ice underneath your ice skates into a liquid. So this is a real practical example of how you can use pressure to change phase. So we think of temperature as changing phase, or you boil water, but you can do it with pressure as well. And this is an example with water. Now and we won't go over this in any detail, but some materials don't behave that way, like carbon dioxide. But this is showing you a different type of phase diagram and how that pressure change from ice skate pushes you up this red line, so you go from a solid to a liquid, from ice to water. Okay. This is ideal gas law, and we had looked at this before, so I won't belabor that. And I did give you a simulator that I think will be helpful. This would be a testable item. You should just know these relationships. You don't need to memorize them, but you should understand the relationships. So because of time, I might, because look at this simulator. That will really help you. Okay, I want to make sure I got to the first law here before I time out. The first law is the energy conservation law, And this, the second law is randomness increases, and the third law is that there's no energy at absolute zero. So those are the three laws. And I wanted to elaborate on this first law for the last few minutes, and then we'll close the meeting, and then I'll give you a start time, which would be it's 10. Why don't we figure we'll start at 10, after this time's out, 10:20, 10:20. So I'll send that by text as well. So we're going to time out here in 6 minutes, and then we'll come back at 10:20 and do heat transfer. And okay, so this is the equation for the first law and a helpful version of it. So there's some buzzwords here. So delta Q, or Q, is heat transfer. And, well, I haven't defined here. E is internal, or U is internal energy, KE is kinetic energy, PE is potential energy, and W is work. So what this is saying is that I can work with all these different elements, and if something is adiabatic, meaning it's not gaining or losing heat, it's perfectly insulated, which is kind of where we'll park for a while. So just pretend this left side is equal to 0, okay, always. I can play with all of this stuff and change things. So for example, if I take energy out of something, if I extract it, something has to give. So either I lower its velocity or I lower its potential energy. So, and the same is true with if I add energy. If I put a turbine into something, I'm going to lower the potential energy, say, of the liquid. If I put a pump into something, I'm going to raise the potential energy, meaning I'll raise the pressure. So if I just look at, for example, these two terms of potential energy and work, I can work back and forth of these with pumps or turbines. So high pressure can be turned into energy through a turbine. High pump pressure can be turned into pressure. So that's this relationship here. Back and forth, okay? But of course, these other things come into play as well, like kinetic energy. So kinetic energy and potential energy, this is the Bernoulli principle. That's these two guys working together, converting velocity to pressure. And we'll look at that in a moment. This is an example of a ball. So a ball raised above a table has high potential energy. Right before it hits the table, it has high kinetic energy, meaning high velocity. Hits the ball or hits the table, bounces back, and it converts that kinetic energy into potential energy. And here's another example of that too. So you're pretty familiar with this kind. Well, you are familiar with this concept, just intuitive. Okay, this is a Bernoulli principle, and it applies in two ways. You're most familiar with it from wings, but you encounter it with Venturis also. So in the case of the wing, what happens is you have a velocity down here that is lower than the velocity down up here. So if this velocity is lower, its kinetic energy is lower than this above the wing. And if we look at now just above the wing, if this kinetic energy is higher, the potential energy is lower. And potential energy, normally you can think of as pressure in this case. So the pressure is lower. And since the pressure is lower, you have a delta P, change in pressure, going this way. Okay. So in other words, because I'm forcing this air to go faster because of its geometry, I'm therefore driving the pressure down. I can't just make things go fast without doing something else. I can add heat, I can add a pump, or I can lower the static pressure. And here, if you look at a Venturi, it's the same sort of thing. If I take all this liquid, let's say, and jam it through, well, let me do a gas. It would be easier for this purpose, an ideal gas. So if I take all this low velocity gas, I jam it through a Venturi, like in a carburetor, the velocity increases. And if the velocity increases, something has to happen, namely the pressure has to go down. So you have a state here and a state here, and if these are adiabatic and there's no energy loss between these two states, when I go into this realm right here, something has to give, and what gives is I'm forcing the velocity higher. So just like the wing, I have to decrease the pressure. And this can actually cause ships to suck together. It can cause flexible hosing to suck in on itself at high pressure. I've heard stories of that in the auto world. I don't know if it's true or not, where high fuel flows can actually cause the hoses to pull in. So we're going to get kicked out here in just a minute. So there's an ugly form of that equation, which has all the terms, and don't be intimidated by that. I might look at that later. I'm just going to, yeah, that's probably a good place to end that. And what I'll do is